Welcome to the next video in the Real Analysis video series. In this video, I am going to walk you over to the Wikiversity webpage and show you how to get to its measure theory course page. So you can just Google or search for Wikiversity. At the main page, you can search for measure theory, and this page should pop right up. And you can go over to section 0, I think it is. And then not the introduction, that's no information, but the lesson 1. So this starts with Fourier analysis. Now we're going to do just the briefest and most sort of informal introduction to Fourier series. We're just, by the way, this is kind of in the discovery phase of talking about these topics. And so we're not going to be very rigorous. We just want to get some sense of motivation. So to start with the basic concept of Fourier series, the whole topic kind of comes from mostly physics, I think, like, thinking about sound waves and light waves and various wave motion, and in particular, how you can understand these phenomena better if you are able to understand how waves can construct, that is to say, if you have like several simple waves, and we'll think about all of these waves as basically sinusoids, like that 2 cosine x, that -3 sine x. And so we're going to be thinking about these simple sinusoids and how if you add them together, you can build up more complicated waves, but also that's the easy direction. And what's more interesting, but also harder, is being able to take a complex wave phenomenon and decompose it into these simple parts. But we're going to start from the perspective of building up from simple parts because that's the easier thing to understand, and it just gives us a chance to kind of introduce vocabulary and so on. So you can see in this, window where the simple sinusoids, if you just add them all together, you get this complex wave. So, the process of going from simple separate waves and constructively adding them together, and there's like constructive interference and destructive interference, but, in any case, all you do is you just add the individual simple terms together to get the more complicated wave. So that's very sort of straightforward. And so, yeah, the hard part is going in the other direction. But keep in mind, when you go in the other direction, the complex wave will not be given to you like this, because that would make everything too easy, right? You would just be able to read off what the simple components are. So you'd be given the wave in maybe like a graph of some function, or somehow you'd be given some data that doesn't look like this, telling you what the complex wave is, and then you have to find some way of reproducing it using combinations of these sinusoids. Now, because we're going to be not very rigorous, then let's make the easiest possible assumption and assume that we have some function which is like the wave, right? Like, so f of x would be the wave that we are trying to model, and we are just going to assume that some coefficients on the sinusoids exist so that f of x is equal to this series. And this is called a Fourier series. And it's probably worth pointing out that the sinusoids are k, right? They have this integer, specifically an integer k, right? So you've got cosine kx, sine kx, and so, we can talk about cosine x because that's with k equal to 1, and we can talk about cosine 2x, that's k equal to 2, and each one of those gets its own coefficient. So a sub 1 goes with cosine x, a sub 2 goes with cosine 2x, and so on. And we're hoping that we can build the function f with these particular kinds of sinusoids. And, in more elaborate studies, we can, make different sorts of choices, but let's work with this for now. So just as a very quick exercise, let's go ahead and take this expression and identify what is a sub 0, what is a sub 1, and so on. So we're getting the coefficients of this complex sinusoid. And so if we look back up at the formula for the Fourier series, then a sub 0, what is a sub 0? It is the one that has no sinusoid on it in a way, right? It's that like very first term in the Fourier series, and since this complex Fourier series has no term that doesn't have a sinusoid on it, then a sub 0 must be equal to 0 in this example. Okay, let's move on to a sub 1. So a sub 1 should be the one that goes with k equal to 1, right? Because that's, with k equal to 1. And that means we're talking about cosine x. And when we look back at the complex wave, right, like the one with 2 cosine x, that cosine x has to be the one with k equal to 1, and its coefficient is equal to 2. So a sub 1 is equal to 2. So there you go. Okay, let's move on to a sub 2. Well, that's where k is equal to 2, so we're talking about cosine 2x. And then when we look at the complex wave, then we see that its coefficient is 1, so that tells us that a sub 2 is equal to 1. Okay, and then so on, right? All the other cosine terms have coefficient equal to 0, so a sub 3 is 0, a sub 4 is 0, and so on. Okay, so all the others are 0. Let's now talk about the sine terms. So with k equal to 1, we're talking about sine of x. In the complex form, it has a coefficient of -3. So b sub 1 should equal -3. All the other sine terms have a coefficient of 0, and so b sub 2, b sub 3, and so on, all are 0. So if we ever talk about finding the Fourier series for a function f, then that means we are interested in finding those coefficients as we just did. That's kind of just what we mean by that. And now Fourier himself found it's named after him because he kind of found a way of finding those coefficients. And he did so because he knew some things about integration that were just kind of in the air at the time, right? I mean, it doesn't take, once integrals are invented and you start calculating some integrals, then it's not hard to show using basic calculus techniques that this equation here is correct, that cosine kx sine nx is always equal to 0 when integrated on 0 to 2 pi. You should go ahead. I mean, that's a good exercise, so I encourage the viewer to pause the video and do that right now to make sure that you understand why that is correct. Now, likewise, if you choose k and n to positive natural numbers, probably should have indicated that it's positive natural numbers like it does above, but in any case, if we assume that they are not equal, then integrating again cosine kx cosine nx, again you get 0. And then if they are equal, right, if k and n are equal, then when you integrate cosine kx cosine nx, you get pi. And then you can show similar facts for the sine functions. But all of these are good exercises, and these are the kinds of things that would have been known to Fourier at the time. So he would see all of these things, and it would, be a bit of an inspiration for how to determine those Fourier coefficients in this, series expansion of f as a sum of a bunch of sines and cosines. The idea is that, well, look, I mean, if you look back at these equalities, when you have cosine multiplied by any cosine or sine term, you distribute it into its Fourier series representation, and then you get things that look like this. So if you integrate it from 0 to 2 pi, then it's going to make most of those things turn into 0, right? The cosine terms, all but one of them turn into 0. The cosine sine terms also, all those entirely turn into 0. Now, likewise, if you choose k and n to positive natural numbers, probably should have indicated that it's positive natural numbers like it does above, but in any case, if we assume that they are not equal, then integrating again cosine kx cosine nx, again you get 0. And then if they are equal, right, if k and n are equal, then when you integrate cosine kx cosine nx, you get pi. And then you can show similar facts for the sine functions. But all of these are good exercises, and these are the kinds of things that would have been known to Fourier at the time. So he would see all of these things, and it would, be a bit of an inspiration for how to determine those Fourier coefficients in this, series expansion of f as a sum of a bunch of sines and cosines. The idea is that, well, look, I mean, if you look back at these equalities, when you have cosine multiplied by any cosine or sine term, you distribute it into its Fourier series representation, and then you get things that look like this. So if you integrate it from 0 to 2 pi, then it's going to make most of those things turn into 0, right? The cosine terms, all but one of them turn into 0. The cosine sine terms also, all those entirely turn into 0. And so now, if you go ahead and compute this integral using the Fourier expansion, you should find that an pi is the result of this integral. And then if you solve for an, you get the formula for the nth coefficient.